Hola, buenos dias. My name is Cheng Li. I'm from the University of Concepcion in Chile. Today, I'm going to present our work about three fundamental principles for engineering the IoT-native software systems. When developing the IoT software systems, there are quite a few challenges and different challenges and complexities. For example, it's quite very well known that the sensors and IoT devices generally have very limited resources and capabilities in terms of compute, storage, and bandwidth. Also, the communication will be expensive, no matter it's in the IoT environment or in the generic distributed systems, right? Actually, more than that, from the infrastructure perspective, an IoT system usually, maybe inevitably, involves heterogeneous technologies and standards employed by different producers, all right? And from the applications perspective, an IoT system will inevitably involve different requirements from the various stakeholders, all right? So given so many challenges and complexities, it has been widely realized that the successful development of IoT native system requires not only just new tools and technologies, but also new understandings, holistic understandings of the systematic development process and its tasks in the IoT environment. So this will require us to zoom out from the technology layer to a much higher layer level view of the development process for the IoT software systems, okay? When zooming out to a much higher level view, we decided to focus on the software engineering principles. According to many more or less similar but different definitions, the software engineering principles are essentially abstractions of the best practices in the software projects, okay? And in turn, the software engineering principles will be able to get the software practitioners to conduct practices in the software projects. If we look at the literature, we can already find quite a few software engineering principles. Several hundreds, I have seen such a survey paper. And some researchers also claim that some existing software engineering principles are still valid for engineering the IoT software systems, which is true. For example, the software engineering principles for distributed software systems, like we should never assume 100% stable internet connections, okay? This is also valid for IoT environment because IoT software systems is also distributed software systems by default. But we argue that this type of principles are still more or less technology side. We would like to, following the previous argument, we would like to really zoom out to the higher level views. Okay, so we would like to summarize and focus on the fundamental software engineering, more fundamental principles. So far we have learned and summarized three fundamental principles for engineering IoT systems. And we name them just enough, just in time, and just for me. Here we have to break the first principle, just enough, into smaller pieces because we have no choice. We have to distinguish between different just enough aspects. For example, we can argue the data amount by minimizing the data collection and by minimizing the generation of intermediate results, intermediate data, okay? And actually, the minimization of data collection has been like a common sense accepted by many governments Okay, it's even a normal regulation in many government policies, right? So because of the privacy concerns. And if we consider the storage of those data, we will have to consider their data size. And we can also consider the minimization of the duration of the data storage. And this can also be related to the privacy concerns. And in this case, there will be an interesting space-time trade-off situation or opportunity here between the minimization of the processing and the minimization of the data duration. For example, for some frequent requests or intermediate data processing, we could probably be able to, using some caching techniques, to save, intentionally extend the duration of the intermediate results to reduce or to avoid the repeated data processing activities. Okay, and the second principle is just in time, and here so far we mainly concerned about the data communication and workload latency. Unlike the first principle, the just-in-time principle doesn't necessarily consider the so-called minimization. Okay, in many cases, probably it'll be worth increasing the latency to get something, some other benefits. Okay, as long as we can guarantee the data to arrive or guarantee the job to finish on time, or at least in time, it'll be worth it. All right. So there will be another space-time trade-off situation or opportunity here between the principle 1 and principle 2. We will use an interesting example to demonstrate some potential practices here. It's quite straightforward. And principle 3 is just for me. This is something quite new, as pointed out by the anonymous reviewers. Okay, unlike the previous straightforward principles, this is relatively new. We argue the awareness of the functional unit or the device's own environment and its own business logic. Okay, we argue though they should be, the different components in the IoT system should be smart enough, but in a very selfish way. I will also use an example to better explain this principle. Since it's also because of the time limit, it's very difficult for me to exhaustively demonstrate different practices for those individual pieces of the practice 1 and practice 2. So I would like to highlight the space-time trade-off between just enough and just in time here. It's just one space-time trade-off situation here. And by referring to some work we are currently doing in our project. Okay, and let's imagine a data analytic job in a very generic sense. We have original data from maybe some sensors or other IoT devices. Okay, and we will need those data to do some analytical tasks. Okay. So this is a very bottom line scenario. We obtain or collect the original data and then we utilize them, analyze them. You see, in this case, there's no extra data processing workloads at all. But this might not be the best practice. This might not be a good option. Okay, considering the very limited bandwidth resources, okay, or expensive communication resources in the IoT environments. Maybe a better option is that we can compress the data at the source side or some intermediate node close to the source side. Then after the data transferring, after the communication, we can decompress them, recover them back into the original form. Eventually, we can still follow the same logic to utilize and analyze them. Okay, So apparently in this case, we will have to pay more efforts. We will have to conduct extra data processing workloads. But in many cases, we will probably get more benefits in this case, and even save more time. Okay, think about we use WhatsApp to transfer photos. All right, the photo quality will be reduced. That's because of the compression. Anyway, so this is data compression technique. And another option is the so-called coded computing. In this case, we still convert the original data into some compact form, codes. In many cases, the data collected can be human-readable natural language descriptions. In that case, we might be able to encode those natural language descriptions into machine-readable bits, bytes, formats data. And then, because they are still machine readable, we can automatically process, we can still analyze them. Okay. Of course, if needed, especially at the user side, we can still deconvert those compact data back into their original form, either keep utilizing them or just showing the results to the end user. All right. So this is the so-called coded computing. We can already find this technique in the literature. A more interesting technique we are working on is the compact data structure technique. Okay, we are trying to apply the compact data structure technique to the IoT applications and edge computing. The difference between coded computing and compact data structure is that let's imagine the previous encoded data or original data are stored like a table. All right, we have data record by record, row by row, and the coded computing is to make the data form compact, but it will still be record by record. Okay, which is very convenient. Even for human beings to recognize, distinguish those data record by record. But if there are also some regular patterns in each of the columns, we will be able to employ some space-efficient data structures to make each column more compact. Then you can imagine that this whole data block, the whole table, will be totally reformed. It will not be record by record anymore. So it will be more difficult to distinguish, to recognize those data records. Then we will have to resort to some specific domain-specific algorithms to help recognize, distinguish data between those records, individual records. And then by using those algorithms, we can still fulfill the data analytical requirements. Apparently, in this case, we will have to pay even more efforts. We will conduct more intermediate data processing workloads. So a very frequent question we received is that, is this really worth it, especially considering the very resource-constrained IoT environment? Well, we have been using the just-in-time principle to not only answer this question, but also to guide our research into this emerging research topic. Okay, as long as we can guarantee the job to finish in time or within a reasonable time window, it will be worth it. And we claim that this technique or this research topic will be particularly suitable for those data shuffling intensive and or the intermediate processing intensive jobs in the IoT environment, okay? Because it can largely save the communication overhead, all right? But of course, there are quite a few different compact data structure techniques. We still need to follow this trade-off, follow the just enough and just in-time principles to get our exploration, to get our investigation into those different compact data structure techniques. Okay, I would like to take this opportunity actually to broadcast our research on this topic. It's quite interesting, but the community is relatively small. We invite more colleagues to join us. Well, unlike the previous two principles that are quite straightforward, the principle 3 is quite new, we would say. Okay, but just for me is to argue that we should avoid or at least reduce the usage of central controllers, any controllers, in the IoT solutions. I will use a conference room illumination scenario to better explain this principle or the so-called best practices, all right? From the literature, we can find that in the current IoT solutions, the orchestration mechanism is vastly employed. For example, the popular public cloud IoT solutions generally require the central controller or central orchestration mechanisms in the cloud, of course, to control everything. Okay, no matter from the data flows perspective or from the control flows perspective. So some researchers already argue about this situation. They say, well, we should be able to make the IoT environment and the edge side smarter. Then what to do? Well, they build up more controllers, local controllers, in the individual or smaller scale IoT environments. You see, still orchestration. So our argument is like, our idea is that can we remove or let's reduce the usage of such orchestration mechanism because it's quite still monolithic. All right. Based on our experience as well as some brainstorming, we finally summarized our third principle just for me. We believe we should be able to make those fundamental unit, the functional units and those devices smarter, but in the very selfish way to at least reduce the usage of the monolithic orchestration mechanism. Okay. Every functional unit or every device will only mind its own business. Right? For example, we still use this conference room illumination scenario that is from the same reference. But in that reference, you will see, I don't show it here, right? You will see the a local controller in their system. But here, I will show you how we can avoid using such a controller. Let's start from the projector. All right, before starting working, the projector will smart enough by technically maintaining a table of the environmental information. All right, the projector will broadcast a semantic notification to the relevant devices in its own environment. In this case, it can be the window shades and the ceiling lights. The semantic notification can be very straightforward, very generic. It's like, I'm going to work and I need a darker environment. All right. After receiving such a, by the way, the projector doesn't have to know anything about how its business partners will work. Okay, the detailed, its partners' work is not the projector's business. Right. So after receiving this notification and sending back the responses, the projector's business partners, like the window shades and the ceiling lights, will make corresponding actions. Close the shades, turning off the light. But they don't really care who sends such a request. Okay, that's not their business. No matter this request is from a projector or some movement detector or the voice detector, doesn't matter. They just do their own business. I make the environment darker. Okay. Okay. To conclude, the whole community needs dedicated efforts, techniques, methodologies, and theories for engineering IoT-native software systems. Muchas gracias. I will see you in the conference. Ciao.